Right.
Nine.
Hello, a very good morning to all of you, esteemed speakers, delegates, and attendees present here and virtually. First of all, I would like to take the honor of welcoming each one of you to the third and final day of Second Asian Symposium on Cellular Automata Technology. After last 2 days' wonderful talks and outstanding presentations, I believe the expectation level from ASCAT has already raised its own bar. That is very justified as we are starting our day with a very special invited talk by Dr. Alyssa Adams. Chairperson for this session will be Dr. Komolika Bhattacharjee. Dr. Komolika Bhattacharjee is an assistant professor in the Department of Computer Science and Engineering, NIT Tiruchirappalli. She received her BTech in Information Technology from Government College of Engineering and Textile Technology, Srirampur, and ME and PhD from IIST Shivpur. May I welcome Dr. Komolika Bhattacharjee to continue this session, please? Over to you, ma'am.
Thank you, Tanushree. Uh, Very warm welcome to the first session of the last day. So today we have the youngest speaker of ASCAT 2023, Dr. Alyssa Adams. Welcome to you, Alyssa.
Thank you.
Alyssa is currently a postdoc at University of uh, sorry Wisconsin-Madison, United States, in bacteriology. She got her PhD in physics at Arizona State University, where she studied the difference between living systems and non-living ones. She also did an internship at Microsoft Research, where they implemented one-shot machine learners directly into Minecraft. For 2 years after graduation, Alyssa worked at Veda Data Solutions, a local data science as a service company focused on making messy healthcare data accurate. Now she develops first and improved software for bioinformatics while studying how complex systems like microbiomes work together to perform robust functions. I have the pleasure of listening to you, Alyssa, in Automata 2020. Yeah, that time. So I have seen your wonderful talk there, and I am hoping that today's talk will be also a wonderful one. And today she is going to talk us about what cellular automata tells about life. So over to you, Alyssa.
Thank you so much for that wonderful introduction. That was great. Oh, sorry. Okay, so I will go ahead and share my slides now. Here we go. All right. If there's any issues in seeing my slides, please let me know. Oops. Okay. Yeah, so I'm going to give a bit of an overview on how cellular automata have been used to tell us about what life is and how life operates. So it also, in addition to being a postdoc at the University of Wisconsin-Madison, I'm currently on leave and I'm living in Kyoto, Japan, where I'm a research scientist at Cross Labs, which is a division of Cross Compass, which is a leading AI firm here in Kyoto, and in Japan. They're based in Tokyo. And what we do is we study artificial life and we study mathematical models to understand more about living systems and how they operate. And our goal is to eventually take these lessons and to build something more, either cellular automata or other mathematical models or computational models that reflect living systems and evolution and intelligence and things along those lines. Okay, so first I thought it would be fun to share a story about my very first experience with cellular automata. So when I was about maybe 8 or 9 years old, we got this computer. I think it was a Windows 95 machine, and there was all sorts of games on it. There was Solitaire, there was Minesweeper, there was this little ski guy where this little monster came out. But then there was also this other game called Life Genesis. And you could see an example of it right here with all these gray squares. And then you can, with your cursor, color other squares either red or blue or even other colors. And as a kid, I was really perplexed about what the point of this game was, because after I had colored the squares, it wasn't a coloring game because you pressed play. And then all of a sudden, the artwork would sort of dance to live. And the longer you watched it, the stranger the behavior seemed to get. And I thought, well, this is really weird. What's the point of the game? How do I win this game? So I went and I clicked on this game tab, and there was a thing that said rules. And I thought, oh, I'll just read the rules. And so I clicked on this rules tab, but they weren't any rules that I was familiar with. Instead, they seemed to be all of these instructions about zeros and ones. And then I kind of closed the program and I thought to myself, well, that's the worst game I've ever seen in the entire world. I don't even understand the rules. So this was my first experience with Cellular Automata. I didn't know they was called Cellular Automata back then. I just thought it was a game that was really confusing, and I didn't know how to win because I couldn't even understand what the rules were. It was a very strange set of instructions there. So I didn't have any other experience with Cellular Automata until I was in graduate school working on my PhD. So when I first joined graduate school, I wasn't really sure what I wanted to study, but then I got this great email from somebody about a new professor called Sarah. Her name was Sarah Walker, and she was starting a lab to understand the origin of life. And I thought, oh my God, that's so cool. What a really neat thing to study. So I joined her lab, and I was really focused on the question of, well, if you're trying to understand the origin of life, how can you understand how living systems are different than non-living ones? Because it seems if there's a gradual transition from not life to life, then you would want to be able to detect, okay, we've actually crossed some sort of threshold to where now this looks a lot like life, and it's not just some dynamics or some chemistry or something like that. And a part of that mission was trying to understand what philosophers and scientists and researchers thought. What is the main difference between living systems and non-living ones? And one of the biggest things that stuck out in the literature was this idea of open-ended evolution. So I use cellular automata models to study what is open-ended evolution, how can you define it, and then how can you measure it in a discrete bounded system like an ECA. So that's what I did for one half of my dissertation, and then the other half was trying to understand open-ended evolution through other systems as well, such as online video games like League of Legends. That was a lot of fun, and so I really enjoyed my dissertation and learned a lot about cellular automata, but I was quickly amazed to learn all of these different variations on what cellular automata are, what they can be, and all the different models that people have come up with. Then after that, I did data science for a couple of years, and then I now currently study bioinformatics, but also study how, like, what are the complexity of proteins, how do proteins interact with each other when a virus is infecting a host, and also how can we understand things like intelligence as a computational solution to problems posed in the environment. I also went to the Wolfram Summer School where I studied more cellular automata. And if you go to the front page of the website, I'm in this photo here, which is really fun because they keep up the photo, and it makes me really happy because I'm just right there on the first page. But that was a really fun experience because I got to interact with all sorts of cellular automata models and really understand the really broad applications for them. And in fact, Wolfram is super interested in this very generalized notion of what cellular automata could be in terms of what rules are and how they evolve states over time with his Wolfram physics project. So I highly recommend taking a look at that because it's a sort of not directly a application of cellular automata, but the same ideas are there, that this is a computational universe and we can understand the laws of physics through that lens. Here's an image of some of the cellular automata systems that I worked with. You have a gray elementary cellular automata and a black elementary cellular automata, and they interact on the same white space. And in order to define how they interact, like these gray and black cells, we explored all of these different permutations of possible rules. And what we saw was all sorts of really interesting patterns of behavior. Also, a fun tidbit, so I did my internship at Microsoft Research in Cambridge. But if you're ever in Cambridge, I highly recommend going to the Cambridge North train station, because the entire train station is covered in Rule 30. So it's the reason why this Rule 30 looks a little bit different is because it's rotated slightly at 45 degrees. But the entire station is just decorated beautifully with these patterns that are just absolutely super fun to look at. So, you know, like I said, if you're in the area, I highly recommend checking that out. It's worth seeing for any cellular automata enthusiast. I could definitely say I look like a crazy person spending an hour while the sun was setting, taking all sorts of photos with my camera. Okay, so to talk a little bit about my long-term research goals, like what am I doing? Why do I like science? Why do I like cellular automata? Why do I like computational models? So if everything works out scientifically, which of course I hope it does because I'm having so much fun, my long-term goals are to really understand new mathematical frameworks for living systems. I'm really inspired by cellular automata and the ideas that went behind to their design and implementation and modifications and variations. But I'm also thinking about what other mathematical models can we come up with? And is there something, is it possible to come up with something that is a universal framework that explains behaviors in living systems such as open-endedness, intelligence, complexity, and evolution? And the approach that I take is I look at the intersection of all of these different fields, the theory of computation, biological evolution, physics, and information theory. And I ask, what lies at the intersection here? Is there a way to understand life as a computer? So the lens that I like to think of it is, you know, even though I have a background in physics, and it's tempting to think that, oh, well, you know, we can think of life as just the laws of physics, and, you know, we can think of those laws of physics as chemistry, and then you get biology, right? A very bottom-up approach. But I like to use the lens that cellular automata have taught me that, you know, life is a type of matter, or you can even say life is a phase, what do you call it? Like a phase of matter that computes rather than being the subject of computation. So usually we think of the world around us as, okay, you have a state and the laws of physics are being applied to that state. And what we see is a result of that computation. But what I'm trying to think of is, rather than matter that is subject to that kind of computation, you have some particular matter that is doing and running its own kinds of computation nested within that. How does that happen? So those are my long-term research goals. So these days, what I'm looking at is I'm exploring all these different models of machine learning models, different variations of cellular automata. What I want to understand is, you know, what can we learn from these models? What can we learn from CA? What can we learn from machine learning that tells us about evolution and intelligence? But also, what can we learn from all the data that's around us? We're living in an amazing era of just tons and tons of data. Everywhere you look, there's terabytes and petabytes of video data, text data, interaction data, all the data you can think of. And I want to understand how we can use that to understand more broadly about living systems, because humans that generate this data are a part of living systems. And So is there something that we can learn about human interactions that tell us about biology more generally, especially about intelligence, which is, of course, how biological entities are performing computations? All right, that's about my research, and that's sort of my journey. But now what I want to talk about is the journey of cellular automata as a model for artificial life. So sort of like a brief history of how they've been used to how they've been used to understand life. And of course, they were invented first to understand biological replication. So the goal of that line of thinking that cellular automata were first invented came from this idea of how can we recreate life from scratch? Can we simulate it in a computer, or is it something that we can make in a lab? So, you know, you have these different programs where you have these creatures that can evolve, and like the dream of artificial life is to come up with a simulation, something like maybe Conway's Game of Life, but something that acts as a terrarium, so which you can sort of run it, and then it evolves, and you come back maybe a couple of years later, or you fast forward it really fast, and then you come back a few seconds later, and it's become something as diverse as what we see on Earth. There's all these creatures in there. They're maybe competing for different resources, and they're evolving and they're changing, and it's constantly innovating. This is the dream that I think came from the original invention of cellular automata. The ideas that inspired its invention really came from this dream of being able to replicate living systems within a computer. And then, of course, there's a lot of approaches that, you know, can we make life in the lab? So, you know, in order to understand artificial life more generally, rather than just thinking about it as a computer simulation, there's this really great talk that Dr. Lana Sinyapayan gave at this really awesome conference on games in 2021, a couple of years ago. So what she does is she explains what artificial life, A-life is, a brief history of A-life, and how it's studied. So to get so you can scan this QR code and it will take you to her talk. So I highly recommend watching it. It's super fun. There's all sorts of really fun digital and artificial organisms in there that she talks about and introduces. So let's see some examples of artificial life to get a better understanding of, you know, not just what can be simulated in the computer, but what different approaches people are taking to really understand more broadly what life is. Because, you know, we can take inspiration from chemistry, and we can take inspiration from technology and other hardware. That way we can think about designing computer simulations much better. So hardware, so this makes me laugh, right? You have this little guy, this lion, he is so funny. So people have been really fascinated with trying to mimic and recreate life from like forever. You have all these strange antiquity devices that mimic animals and strange behavior. This is something that was designed by Leonardo da Vinci. So you can see like some fun examples of people have just always been really fascinated with that, right? But then you also have these really amazing robots that are being created that are trying to mimic movement. So this robot here, it mimics the movement of the human who raises his arms up. And then the robot is, so the robot's mimicking the human, but also the human is mimicking the robot. So between this interaction, you have a sort of dance between the robot and the human. So you get these different kinds of ways of interacting with technology. Like, how can we build a technology that is in the physical world that mimics at least humans or other living systems as well? And then, of course, you get these other kinds of devices. A-Life is also about how can we outfit our current biology with technology that enhances what we can do. So, there's this brain implant, and there's this very intimidating looking machine that you can stick your head in, and don't worry, it's totally safe. You'll be fine. Um, so, this is also on the horizon as well, is augmenting our own biological capabilities to have these, different modified technologies. So that's also a part of artificial life, is how can we use technology as an extension of biological evolution. It's scary, so let's move this slide. Okay. And then of course you get not just things that are technological, but you get things that are completely biological as well. So here's these famous xenobots by Josh Bongard and Mike Levin, and I think this gives a new meaning to the term cellular automata, because these little guys are made of frog embryo cells, and they're in a shape, and they sort of dance around, and they collect all of like these specks of cells that are hanging out. And as they collect these other cells, these other cells form bunches, which turn out to be more of these shapes. So you have a sort of mechanical replication, if you will, which is really fun. I think that this is a really nice example of how you can think of computational models as applied to biological technology. And I think there's going to be a lot more examples of this in the near future, for sure. And not only that, but you can say, okay, I have a grid-like world, right? But instead of taking these virtual cells of black and white squares, maybe you put brain cells on there as well. And you can train that grid of brain cells to do tasks. Like in this example, they have trained these brain cells to play Pong, which is really quite amazing, because here you have a system that is a lot like the cellular automata worlds that we know and love, except it's instantiated into the physical, biological, computational intelligence realm. So it makes me wonder, are our brains acting like cellular automata, and how are the interactions between neurons contributing to our overall capacity for intelligence? And right, so then of course software, right? We're going to talk about cellular automata. Of course, can't miss that. Here's the game of life. People have done some really incredible things with the game of life. Here's an actual computer instantiated in Conway's game of life, which I'll come back to because I think it's really, really important for artificial life. But then you get these really crazy patterns and structures. Like what? I mean, people make a whole hobbies and jobs and professions out of designing these absolutely incredible, intricate machines in the machine. And the reason why this is possible is because you have the game of life is Turing complete, which means you can simulate really any kind of computation, even if it's extremely slow. But you can see, like, I mean, look at this stuff. It's insane, right? All right. I felt like I had to include this video because it's my favorite. And then you get other kinds of cellular automata that people have designed for artificial life. So you see here, the grid is getting, I'll rewind it. So you have like a regular cellular automata grid, many different states than just two, and then you make the grid smaller and smaller until it becomes continuous. And so what you have is you have a continuous cellular automata, and you can see things like gliders still, even in this sort of system. And, they even look like jellyfish, and then they collide with each other, and it's just all sorts of fun. And we'll play with this more later on in my talk, just because this is a really important system for understanding how living systems work and how creatures might emerge. So it's just a preview for what's to come. And if you're interested, you can go to this website, curly.org. Has a really great list of additional artificial life software. But please note, as you're exploring these, a lot of these are built on these very basic fundamental ideas of cellular automata. So I have yet to see a piece of software that isn't very, very close, at least just a few steps away of modification, that is a cellular automata based. So that's the software in artificial life. Okay, so that's artificial life. And those are the goals, and so those are the kinds of things that are out there in trying to understand how can we capture aspects about life in computer simulations, technology, hardware, and how can we hack living systems in order to do our computational bidding, as you will. Okay, so more specifically about cellular automata, right? There's so many different variations and so many different kinds, and they have such a really cool, rich history. So of course, we're going to start at the beginning with Stanislaw Ulam and John von Neumann. So in the 40s, Ulam, he was really interested in crystal growth, and he came up with this idea of having a discrete automaton on a grid-like world, a two-dimensional world. So that's his contribution. And von Neumann, he was really interested and has been interested for a really long time in this idea of self-replicating robots, because this is the age where computers are starting to dominate technology, and people are really starting to think about machines as, wow, they have a lot of potential. How lifelike can we push them? And von Neumann was one of those people who was trying to push computation to its limits, and really understand what will it take for us to have things that are self-replicating. So this is the model that they came up with in the 50s, and it was a two-dimensional cellular automata with 29 states. Can you believe 29 states? That's crazy. And it was a model to describe the liquid motion, the motion of a liquid on a two-dimensional surface. And it was a successful model. You can see it implemented here. And you can, I plucked this from Wikipedia because this is also a really nice example of showing you have some idea of replication going on here, where, I mean, it might not actually be replication in the way that John von Neumann was thinking about it, but you still have something where you have something being appended as a chain. And then you have this sort of program that is instantiated in this loop here, where you have a 1011 sort of instruction code that goes around it. So John von Neumann was really interested in this idea of taking a pattern that would make endless copies of itself. So, and he called it his universal constructor, right? And the idea is that you want to have a machine whose complexity is going to grow automatically with every generation. So not just something that replicates, but it's also growing in complexity, just like biological organisms when they undergo evolution under natural selection. And he was really interested in thinking, okay, is there some sort of threshold of complexity that needs to be crossed to get here? Because we have simple machines, right? But they're not really that complex. So how complex do we need to make them in order for them to take off just like biology takes off? And this is really a origin of life question as well, because when we're thinking about the origin of life, we're thinking about, okay, how are these chemical reactions going to be complex enough in order for them to start evolving and changing over time? What does that look like? What sort of complexity threshold is there? How can we reach it? So, but he was thinking about it in terms of computation, which I think is a really inspiring way to think about it, because at the end, chemistry really just, I mean, from my perspective and many others' perspective, chemistry really just is a medium to perform computations. But it doesn't even have to be in chemistry, right? Because if it's something that can be thought about in computation, then we can just abstract away the chemistry altogether. And there is the possibility that something like this could happen in a very large, perhaps very large digital space. So he wants to know how to do that. And what you can see here is you can see an example of this universal constructor running. You have something that is a machine, and then it starts to copy itself over time. But what you don't see here is you don't see it increasing in complexity. And that was something that worried him because he wanted something that increased in complexity. So he looked towards the mechanisms in biology to design, to further refine his models of cellular automata. And this is what he thought of biology as being something that's computational. So he thought of it as a set of instructions here, which is like DNA, right? And then he also thought, well, okay, you don't just have DNA, but you also have some sort of mechanism that he called the universal constructor that takes this set of instructions and executes it. It builds it. So this is the central dogma in biology, where you go from DNA, and that is a transcription process, and then you get proteins. And not only that, but there's also some sort of mechanisms hidden within these proteins that is universal copier. And what that copier does is it copies this set of instructions. So, which in biology is this idea of when the cells are splitting apart, they're not just dividing their own material, proteins and stuff, but they're also copying their own genetic material for one to go onto one side and one to go onto the other side. Of course, and then there's all these other operations, like the basic mechanisms of the cell, and then some extra functions, such as how these cells interact with the world around them. And the way that this works is you have your set of instructions. It gets transcribed and executed into some proteins. And then you also have the set of instructions that get copied. And what you get is you get this new cell. So he was really inspired by the idea of how biology replicates and grows in complexity over time. And so he wanted to put this into the cellular automata. And as a result, that's what you see these cellular automata models that we know and love today. It's not a direct, it's not, like, a lot of it was abstracted away into this idea of having a global rule, but the basic ideas are still there. This idea was inspired a lot of thinkers and scientists, and there was this groundbreaking book in 1969 called, see if I could say it, Rexner Ram, which translates to calculating space. I totally did not say that right. But basically, the argument was that all processes are computational. The universe is a computational one. And there's this idea that everything can be simulated. Perhaps we're being simulated, but you can think of all of physics as being a digital process where you have the medium, which is matter, and the laws of physics are this like program that is being executed on this matter in order to come up with more computational things. And then this is also the birth of pan-computationalism, where there's this idea that everything is computable or some result of a computation. And then cellular automata get further developed and they make it into popular culture. Of course, we're looking at John Conway's stuff here, which is super fun. But so this is the Turing machine that I wanted to show you. People can really, really come up with some elaborate things here. And so the main driver of doing computations in Game of Life is the presence of these gliders. So you could take gliders, and if you have a glider gun and you shoot them in a particular way, you can get sequences of ones and zeros, or really just any signal to do your bidding. So here's a universal Turing machine, which was instantiated in the Game of Life, because this is something that is Turing complete, which is very exciting. So let's dig into this a little bit more, because I really like computers. I really want to see what a computer in Game of Life looks like, and what you get. I don't want me to skip over this. Yeah, so you get, using gliders and glider guns and different ways of interacting with gliders, you get a finite state machine. You get oops, pause it. So you have your Turing tape here. And of course, it's not a true Turing machine because you don't have an infinite tape, right? But you have it approximated to a finite state machine. And you have this array of signals and a way of interacting with the tape such that you can approximate your Turing machine. Whoops, I did not mean to skip over. Oops, sorry. Okay, yeah, cool, right? And then so you can expand that idea a bit more and turn this into a computer. So you can build a computer in the game of life using this idea. You have your memory card here, which is going to store your bits of information. You have your ALU, which is your algorithmic logic unit, and it's the thing that's basically the CPU, which is performing the computations. You have a program that is executing that is the set of instructions, and you also have a display here, which is amazing. And you can make this really big, and you can even make a clock here. Oh wait, go back to the clock. So this is crazy, right? You can absolutely do this. You can even program Minecraft into this because of everything, because it really is truly Turing complete, and you can do anything in it. You might just have to speed it up, but I think one of the most amazing things about this, which is recursion, and one of the most biological things to me, is you have this idea of, okay, can I emulate Conway's Game of Life in Conway's Game of Life? And you absolutely can. I'm going to go a little faster. So you have all these gliders here, and you have all these different barriers. But if you set up your barriers in your grid, like the lines that actually make the grid correctly, then you can actually make the structure of those of that grid to hold in the program of the rules of Conway's Game of Life. So when you zoom out, you get Conway's Game of Life and Conway's Game of Life. And I just think that is just so dandy and so cool, and also so relevant for living systems, because, you know, in this larger picture, you do have a global rule of Conway's Game of Life, right? That is doing the very elementary, very basic computation, or like movements and dynamics. But on this larger level, that is getting programmed into the actual structure itself by means of these lines that make up the grid. And I think biology is also something that does this, where it is not just being subject to the laws of physics, which is like this global rule, but it is also encoding additional rules into its own structure. So I think this is extremely inspiring for trying to understand how life operates and how it evolves, right? Okay, and then so we're going to the 1980s now, so that's super cool. And then Wolfram, he does this amazing work in his very big book, New Kind of Science, where he breaks down elementary cellular automata into, I mean, it's basically a elementary cellular automata Bible, where he talks about the 4 different complexity classes. And in particular, he focuses on the computational power and a new paradigm for understanding how we can think about the physical world in terms of computational paradigm. In case you didn't know, there is I hope you all can see this webpage here. There is a Wolfram Rule 30 prize going around that specifically talks about Rule 30. But if you can solve these 3 questions, these 3 problems, then you'll get $10,000 each. And if you do all 3, then you get $30,000. And take a little sip there. All right. Back to these slides here. Okay. Right. So that's the history of cellular automata in terms of how it's used to understand our life, and particularly artificial life. So since then, what have the major advancements in artificial life from like how have cellular automata contributed to like recent epiphanies about how life can be emulated and created from scratch, right? Well, in terms of the different cellular automata models and variations that have come out, There are so many, and there are way too many to enumerate in this talk right now. But what I'm going to do is I'm going to talk about three, I guess, different approaches and examples that have been really useful for understanding life. So I hope you all can see this. Is sharing a window. Okay, yep, hopefully it should be sharing this. All right. And one of the biggest advancements is this idea of neural cellular automata. So this is the idea that you still have a global rule. That rule applies to every cell and every neighborhood type. But rather than having something that's like a I don't know, like one of the rules that we all know and love, what if the rule was like a neural net? So a neural net and all machine learning models are basically just functions, right? You go from input to output, and then there's all these like layers in between. So that function is the rule. So you have a neural net that is your rule, and you have three different kinds of rules here in this nice little web demo. It's super fun. You should try it for yourself. So you have growing. You can grow these lizards, and oh, I accidentally destroyed it. That wasn't too good. Let's see if we can chop it in half and grow 2 parts. Nope, I'm too mean for that. Okay, well, let's try persistence. All right, and this means that can it persist? Can it remain? So if you know that if you destroy too many of it, then it goes away. But regeneration, I think, is one of the most interesting ones, because in one of the big questions in life is how does information get stored in a body or in a physical state such that that information can be re-executed at any time. So this is super fun. You can just go right through the middle of the body, and according to the cellular automata rule, it can regenerate and maintain this state just fine. So maintaining a state in living systems is super important, because that brings up all sorts of questions about homeostasis and, of course, how individuals continue to persist and maintain themselves. Just for funsies, let's go over to the fish here. And this is fun because you can, through this process of regeneration, you can even extend the fish, or let's see. I was able to get it to do it last night, but I might not be able to get it to do it now. Maybe it's, oh yeah. Yeah, these cellular automata models do all sorts of crazy things. That was fun. Anyway, so yeah, you should try it yourself. It's a really fun toy. Really cool cellular automata out there. So let's go to another example here. So there's a lot of amazing artists who do all sorts of amazing things with cellular automata. So people really like, this is one of my favorite artists, Slackermans. He does some really amazing things with cellular automata, and really you can just sit here and watch these for so long. They're so beautiful. They make so many amazing patterns. Some of them really just are looking, it feels like you're looking into a microscope and looking at some pond water, which I think is really amazing. So you have a lot of artists who are doing this, and of course there was the earlier in the conference, there was a big part of big part of the conference dedicated to art, which I think is great. So this is another person to follow if they hadn't been mentioned already. And then example number 3. So I'm getting back to this idea of Lenya. So this is the continuous cellular automata model here. And you can play with Lenya in your browser, no problem. But what I think is really fun here is they've made a sort of biological classification of these different kinds of organisms that you see. So not just gliders, but you can't start with gliders. Let's go to Conway's Game of Life here. And you got your classic little glider that everybody knows and loves. You can make a glider gun as well. But then you can smooth life out, and this is what you get when you smooth it. But then you get all these other different things as well. So let's go ahead and pick you have some things that spin, you have some things that move, you have some things that sort of flutter around. You get oh wait, no, this is Conway's Game of Life, my bad. Yeah, But you can just go in, you can go in here and see all the different quote unquote species that have emerged. They're super fun. All right. So, and I don't want to run out of time before I talk about, all right, yes. So, okay, these, like I had said, like it reminds me of looking into a microscope and looking at pond water sometimes. So obviously we're all wondering how close is these artificial life models to real life? Because they look like life, they move like life, they have a lot of variety like life. So in some ways, it is very close because it looks very similar. But in other ways, it's not capturing some aspects of biology. So at the end here, I'm going to talk about what's missing. And I mean, there's a lot of things that we still don't understand. We still have a lot of work to do, a lot of different models to consider. So the things that we don't understand, this is a short list, by the way. So we don't understand all the mechanisms that are driving evolution. And a lot of it has to do with the interaction, not just between living systems themselves, but also a very rich environment that contains tons of living systems. So different kinds of living systems, and living systems also do things like terraforming and changing their atmosphere and just changing the very basis of what their environment consists of. Well, of course, we don't understand the origin of life, but we don't also understand the origin of information, the origin of computation, if you will. What makes it possible for living matter not to just process information, but to come up with new ways of processing information and to come up with new ways of computation. What makes it different? Of course, what makes life different than non-life? What would it look like under a different chemistry and all these different things. But the big thing that still sticks out is this thing from my dissertation, which is open-endedness. And that is still something that if you ask some people, they say that yes, it's been solved, but a lot of people say no, that it hasn't. So I'm going to talk a little bit about the overview of what is open-endedness, right? And Ken Stanley is a really great person to see his videos and read his essays and his papers and see his research on, because he's thought a lot about what open-endedness is. And he calls it this never-ending algorithm in this amazing talk from Good AI. And basically what he's saying is that one run of evolution on Earth gave all of this amazing variation. And there's no human intelligence involved in it whatsoever. And, you know, even if you, and we even ask, like, if we were to rewind the tape of time and replay this, would we get the same kinds of organisms? So we get endless surprises. And this sort of process is what we call open-ended evolution. And it's different kind of learning. It's not just it's can be considered a type of intelligence, but it's not the kind of intelligence that we see in machine learning, because we don't just get one positive result like we do with machine learning. It's like, oh, okay, we've trained the model and now it can perform this function. That's great. Biology takes it one step further, and it continues to evolve, and it continues to pick up new things that it can learn, and it also forgets things, right? So we still don't have this, and we still don't totally understand how we can get this. There's this really great essay that he wrote called It's the Last Grand Challenge You've Never Heard of. And he talks about how this understanding open-endedness may even help us understand things like general AI, or if you don't like the term general AI, the idea is basically how can we get to general learning rather than specialized learning, because systems that are open-ended don't just solve problems, right, that are presented to them. They're also coming up with new kinds of problems for themselves to solve. Sort of like humans, right? We're not just solving problems, but we're constantly creating new problems. And that's one of the key aspects about open-endedness. So there's just tons and tons of debates about, like, okay, so that's a great idea. How do we turn that into something that we can measure and something that's a little bit mathematical? That is a huge topic of debate that is still ongoing. There's multiple workshops that talk about the nature of open-endedness. And here's a really nice diagram that sort of summarizes the unfortunately complex and nuanced perspectives that all these different researchers are bringing to this topic. So there's, but what you can see is there's these different notions of dynamic hierarchies. There's evolutionary processes. It has to do with novelty and diversity, adaptation, different kinds of entities, complexity, of course. Maybe there's some dynamic hierarchies, different kinds of interactions, and this idea of interestingness, which is also difficult to define. And in terms of how you measure it, well, there's a ton of different ways to measure it as well. And unfortunately, the picture isn't any clearer for trying to understand, trying to get to a single standard of trying to measure, well, how open-ended is it? How do you exactly measure these kinds of things? But despite all of this debate and difficulty understanding and coming to an agreement about what open-endedness is and how to measure it, there is a good sense of that there's different levels of open-endedness. Sort of like one of these things where we have an intuition about, but we don't fully understand mathematically yet. So we understand open-endedness on a kind of spectrum. So you have a weak open-ended, and then you also have strong open-ended. And weak open-ended is examples such as counting to infinity. So as you count from 0 to infinity, you're always coming up with new numbers, which is innovative, and every number is a new thing, and you might even grow in complexity. But the process that's underlying this generation is exactly the same. And that's not quite satisfying to the people who think about open-endedness. This is the same with crystal structures. Well, you can get all sorts of really interesting crystalline structures that have beautiful shapes that are really continuously growing and growing in complexity. However, if you zoom in on the atomic structure, there's a very low atomic complexity there. And then again, the process that generates these shapes is exactly the same. Same with something like a double pendulum in physics. You get a lot of complexity, but you don't have anything that's necessarily innovative in the sense that our intuition says it's innovative. Although that there could be a lot of arguments to that, and I'm open to hearing and different points of view there. So then, what's strong open-ended evolution? Well, biological evolution is our best example. Because not only are there new structures and new functions, but there's also new genes and new ways that these structures interact with their environment. So not only are they changing their structure over time, just as we see in Conway's Game of Life, but they're actually changing their rule. So in some sense, they're changing, maybe not changing the global rules of physics, but they're coming up with new kinds of functions that determine their behavior. So take humans, for example, we're obviously bound by the laws of physics. However, we're able to synthesize atoms that have really not been seen in the universe anywhere close within light years. If you look at the periodic table and see the things that we've been able to synthesize in the lab, obviously extremely difficult to do without humanity and ingenuity. However, because we've come up with our own rules of how we can really bend and focus in on particular areas of the laws of physics, we're able to reach things that would be really difficult to reach naturally. So human society is all about this. Like the rules that we create, our laws are always growing and changing over time. And same with our ingenuity, our technology. These are really good examples. But even if we think about the example of biological evolution, you do get things that are repeating exactly over time. Or you don't get things that are repeating exactly over time. You get a lot of changes in the genotype and the phenotype is growing in complexity. However, there is still a lot of debate as to whether actually even biology itself is open-ended, because we haven't been around long enough to see if it's actually going to repeat. I mean, maybe it repeats on a 5 billion year cycle. I don't know. Like we haven't been able to see it. And people even question, is the universe open-ended? Does it actually repeat? So in terms of like, okay, going back to questions that are testable, can we make open-ended systems in artificial life models such as cellular automata? Some say yes, because they say open-endedness is actually really easy to achieve. And we have many methods that result in open-endedness, like people would say linear. And if you have an infinite grid in the game of life, like, sure, yeah, that's open-endedness. However, the outputs just aren't as interesting as what we see in biology. And Joel Lehman talks about this really great analogy of a bowl of oatmeal, right? So you can have a billion bowls of oatmeal, and they're all technically different. They're all atomically different, and you have different configurations of those oatmeals. But at the end of the day, they're just bowls of oatmeal, right? They're not necessarily very interesting. So, and some say no, that we haven't actually satisfyingly cracked the puzzle of open-endedness. And the strongest form of open-endedness, it's biological evolution, and we haven't created anything that can achieve anything as close as that in a closed system. But of course, this also depends on how picky you are about your definition of open-endedness. And this lack of having a agreed upon definition of open-endedness is starting to become a hindrance in terms of how we can understand what our models need. But here's another prize for you all. $100,000 evolution prize still has not been claimed. And if you can demonstrate open-ended innovation in a closed system, then you can claim it. But so far, nobody has been able to claim it, even though there have been many attempts, perhaps due to the lack of agreement about what counts as a satisfying solution. But so that's still out there. So in conclusion, basically, there's a lot of things that we don't understand about biology. And if we don't understand them about biology, then it's really hard to put them into systems like cellular automata. But at the same time, exploring different systems like cellular automata can help us understand how different mechanisms happen in biology. But because, of course, it's easier to modify a simulation rather than doing something in the lab. And thank you so much. And I wanted to share this last picture of the seashell, which looks like a cellular automata. I got it in Mexico. Super fun. I've only seen them on the internet, but when I came across it in Mexico, I was like, I need to buy it. So yes, you too can find one. Thank you so much. There we go.
Thank you, Alyssa. Thank you, Alyssa, for the interesting talk. I believe our young and audience will be more interested to do research in cellular automata after seeing this journey, starting from the one human and going to the open-endedness and what remains to be done. Yeah. So any questions from online and offline audience? Yeah, we have questions.
Very, very interesting and amazing things. I have been watching this, but the life is matter that can compute. You started with this. Since life is in the domain of biology, the computations in biology, I think mathematics is not yet ready to capture all the computations in biology. That is, of course, I have gathered this idea. Not only that, the old man, the Knuth, stated that to explore all the computations in biology, it will take another 500 years. I don't know why he has said 500 years for this purpose. Thank you.
Very cool. I totally agree. There are so many computations in biology, and I really don't think we'll have the capacity to compute those things. I think that, we could think of biology as being a really big computer that's been running all these computations. And in order to come up with these computations ourselves, essentially we would have to build a computer that is as big or as powerful as biology. However, biology is something that spans and covers the entire planet. So I think there's going to be definitely some sort of issue there. I mean, I mean, like, my science fiction brain goes, well, we can maybe turn the moon into a big computer or something ridiculous, right? But yeah, I think you're absolutely right, and we cannot uh, compute everything that biology computes. And is this something that is a problem for computing any aspect of biology? I sure hope not. But it is a possibility that, in order to compute any aspect of biology, you have to have the whole system, because it is so intermeshed with each other that it might be impossible to entangle. Something we're still trying to figure out. So who knows?
So, any other question? Yeah.
Hello. Hello. Ma'am, this is a very nice and interesting talk, but my question is like, an artificial life. I have studied some of artificial life property that a machine, if a machine can mimic some self-replication, self-organization, then we can relate to that to an artificial life quality. But my question is related to intelligence of the machine. What is the threshold of intelligence? Can I say if a machine can replicate itself, it is intelligent? Or can I say a machine have an affinity, it is intelligent? Or all these property need to be there to become a machine intelligent? That is my question now.
That's a really good question. So, um, yeah, that's a really interesting question, because I think that we're still trying to understand what intelligence is. And I think that your question is extremely valid. Like, if something can replicate and grow, is that considered intelligence? And then what threshold do you need to cross in order for there, or is there a threshold at all? That's entirely valid. And unfortunately, I don't have an answer for that. But because I think because I don't really understand what intelligence is exactly. Like, how many neurons does it take, or like what sort of computational capability is it? And I think that's something that researchers in general are still trying to figure out. I tend to not think of intelligence in terms of something that may be a quality that we possess, but I tend to be a lot more liberal in thinking about, okay, forget the word intelligence. Let's just think about computational capability, and how powerful is the computer, and how powerful is this machine. And if you take that approach, then you have things that are very, very simple. Cells have some sort of quote unquote intelligence because they have a computational ability to solve problems, like interact with their environment, and also to replicate as well. So yeah, I think that's a good approach to think about I personally think it's good to think about intelligence as being, yeah, you can be really liberal with it and say that if it is replicating, it does have some sort of quote unquote intelligence, but it's definitely not the kind of intelligence that we humans think of when we think of ourselves as intelligence. Like, we think, oh, I'm intelligent because I can do mathematics and writing and whatever, but that's not the same kind of intelligence that is a more broader thing, where it's just thinking about computational capability of an object.
Okay, so yeah, going into that line of question of Subroto, probably he's asking like, what are the properties that you think that machine should have to be an intelligent, to be called intelligent? Probably that is what he is trying to ask you. Any comments on that?
Ah, so yeah, because I'm so broad in terms of thinking it. I guess what I would say, if I were to just take a shot in the dark that's based on absolutely no scientific basis whatsoever, I would say that something to be considered quote unquote intelligent, the way we would think of it, would perhaps would need to be able to compute in different state spaces, I suppose. So what makes humans really special is our ability to come up with new ways of communicating and really inventing new channels and new ways to compute. I think a system, in order to to be intelligent, in my very armchair opinion, that's what something would need to do. Is it would need to learn very quick. It has a lot to do with learning, and it has a lot to do with inventing new ways to compute on its own through interactions with the environment. So
So we have a online audience. We have a question from online audience. I think it's Professor Goel. Uh, Dr. Goel, can you please read out the question?
Yeah. So my query is that am I audible?
Please continue.
Am I audible?
Yes, sir.
Okay, all right. So can we really use CA for some serious computational and number crunching task efficiently? Like, can I use CA to find the second largest element in a given list? Apart from the fact which I understand is that rule number 110 is a universal computer, and we have already talked a lot about the philosophical stuff. So my query is related to the serious, efficient, computational and number crunching task carried out by a cellular automata. Thank you.
yeah, so I'll say yes and no. And I think that no right now because our a bit I don't know too much about that kind of literature, but I do know just from watching people build like computers inside these things that it runs really slow. It can run really slow, even though it's Turing complete. It doesn't mean it runs super fast. However, I also say yes because I think there's an incredible capacity for these systems to carry out parallel computation. And I also looked at this area of research called DNA computation, where they've utilized DNA to carry out different computational tasks, but also to store information along the DNA structure itself and to read and write via transcriptional processes. And it's extremely fast. However, that's only after you get it all set up, because the problem isn't in the system's ability to read and write really quickly in a parallel way. The problem comes from our ability to translate it into something useful. So I think for cellular automata, if we're able to work with these systems to come up with a way to translate whatever dynamics is going on in a really quick way, and maybe something that is able to be abstracted a little bit and to be extended, then I think we can absolutely do it. But yeah, that's something that I'm actually really interested in looking up, and I'll do some reading on that as well. Have people looked at that? I'm really curious, because I definitely do think that there is the capacity there in order to do some really serious computational number crunching because of this way that they can be parallelized in a very large grid. We just have to come up with a way to read them and to make sense of the information in a way that's really fast and efficient, rather than waiting for one glider to scoot all the way across to the other side. Can we look at it from like perhaps a top-down perspective or something like that? So yeah.
Thank you. Thank you for such an elaborated answer. Thank you very much.
Okay,
Cool
so
question.
I have one last question for you from my side. As you have shown us some game of life patterns and beautiful patterns and explorations of different versions of life that is done by the life community. But my query is, all these are done on infinite grid, right? Infinite lattice. But if you consider any computer, that's basically a finite machine in some form. It's a limited amount of memory, space, and all. So where our cellular automata will lie if we want to limit that to a finite space, limit our CA to be a finite system, having a finite number of cells. So what it can do? Can it do the universal computation? what it can achieve, how far it can be in the domain of artificial life. That
Mm.
is what is my question.
Yeah, I think that is has a lot to do with the limits of Turing machines, thinking about Turing machines, because of course, so a Turing machine talks about, okay, you can have a universal Turing machine, which is a Turing machine, but in order for that to happen, it has to have an infinitely long tape, right? However, there is no such thing as an infinitely long tape, but we design our computers based on this assumption anyways, and we still get along fairly well with that, by building more and more powerful things. So the assumption is that if we have a computer that's big enough, we can interact with it just fine by assuming that it is a finite tape and it is a Turing machine, and our computers still operate just in the same way. So for cellular automata, I think it's almost the same. Practically speaking, we would just need a grid that is large enough, right? And we need a grid that is so large that we don't ever have to worry about running into this kind of space. That's for computational feasibility. But in terms of artificial life, do we need an infinite grid in order to really realize living systems? And I think thinking about the living systems here on Earth, our grid that we live on is really, really large, but it isn't finite. It is a something. It's we're still on a globe, and we're still confined to a space, even though that we also have things that are interacting with us from the outside. So I think with that consideration in mind, if we have a large enough space, I think it's still very useful for artificial life, and for having a cellular automata that is in a super large space. I think for understanding living systems, it's going to be okay because, like I said, our life isn't in an infinite space, even though that, of course, the human population is going to try to leave and try to explore the infinite space in the near and far future, I'm sure. So I hope that I hope that answers your question. That I don't see it being a problem, but I also do recognize that it is something that we are constantly looking to expand our computational capabilities. And at cellular automata, that what that means is we're looking for larger and larger grids to perform our computations on.
Then, if you are taking a finite system, obviously it's going to have a boundary. So, are you going to consider open boundary or periodic boundary for that? Because that will lead to the open-endedness problem, might be. So, what you will be considering as, what should be your preference as for as you think?
Hmm. I think both have a really good, both have pros and cons. For having a bounded system, trying to find open-endedness in a bounded system is really important because a lot of people consider life, like on our planet, as a bounded system. So if we can try to understand open-endedness in a bounded system like that, that'd be great. However, a lot of people are very skeptical on whether or not that's actually possible, because even if our life, even though it is bounded, we've still had like meteors and asteroids hit our planet that really affected our evolution. And of course, we get all of our energy from the sun, which is outside of the system. So it's not really a closed system in many aspects. So I think there's a lot of merit for trying to look at open-endedness in a closed system. But I also think that looking at an infinite or something that is extremely large, at least, might be more, might be easier to think of open-endedness in a larger system. But of course, but then I go back to the other thing of like, it would be more interesting to get open-endedness in a closed bounded system, just because that's the harder thing to do. Can we do it?
Okay, thank you for the interesting talk. So, with this, oh, there is a comment from Genero. I can't read out from here. Uh, Gen- Genero, can you please?
Okay, hi. So, thank you very much for this interesting talk, Alyssa. Uh, my question is about of this open-ending perspective. I don't know if you think it is related to controller a complex system. For example, the game of life. Using this complex system can be used to increase its own complexity and then increase again the complexity. It is right or not for open-ending perspective?
I think that is a really good approach. And I think that's an approach that is more close to biology than other approaches because if you look at all of our open-ended systems, like for example, the economy, the stock market prices, one could say that that's an open-ended system, and many do. And that's driven by other open-ended systems. And those open-ended systems are driven by other open-ended systems. So I think it's a really good, really good approach. The problem is more theoretical of how many different layers of control do you need in order to get something that's open-ended. But if you're also thinking about the origin of life, is where is the first layer of complexity coming from and how does that come from? But I think if you're going to engineer something that is open-ended, I think that is the easiest way to go, is to have it driven by something that is also complex. Maybe having that thing driven by another complex thing and that thing driven by another complex thing is certainly possible. So but yeah, again, I think that it also raises the question of where does the first layer come from and how do you get to the first layer, and also what is the threshold for having these, like what is the threshold of complexity for these different layers? Do you need one really complex layer, or can you have just like a million simple layers? Those are really interesting questions, and I think that it would be a really cool line of research to go through that.
Okay, thank you, Kamalika.
Thank you, Janaro. Okay, so with this, I thank Alyssa once again for joining us online and giving this wonderful talk. We hope you will be coming into India next time and join us offline. Yeah. So, yeah. With this, I close the session. Thanks, Alyssa.
Thanks, everyone. Bye.
Thank you, Dr. Kamalika Bhattacharjee, for this wonderful session. Now I request Dr. Shukanto Das to present Dr. Bhattacharjee a memento on behalf of the ASCAT team. Now let's have a small break. We shall assemble here at 11 a.m. Online participants are also requested to join at the same time. Thank you for joining.